quick compare and contrast between discrete probability distributions and continuous ones. You'll notice continuous probability distributions are formed by smooth functions, right? So the graph looks like a smooth function. Discrete ones look more like these rectangular histogram type drawings, right? In a discrete probability distribution, you can find the area of something like the probability that x is equal to 5, and that's because 5 on the number line would actually represent the space from 4.5 to 5.5, and then it would have some height. This means that we have a rectangle, and that rectangle has an area, and the probability that x is equal to 5 will be proportional to that area. On a continuous curve, we're not able to say that, if a here was 5, we wouldn't be able to say that you let 5 range from 4.5 to 5.5. We can't do that because 4.5 is an achievable value on a continuous probability distribution. In other words, the measurement could turn out to be 4.5. Here, for a discrete probability distribution, that wouldn't be possible because you might be talking about, say, the number of people out of 10 who do something. We can't have 4.5 people do something or 5.5 people do something, right? So it's just 5, so it's okay to allow that interval to range from 4.5 to 5.5 because 4.5 and 5.5 are not actual data measurements that you would encounter. Here we can't do that though, because somebody could have a measurement of 4.5. Say that was the length of someone's index finger. It could be 4.5 inches, and that would be different from having one that's 5 inches. So you couldn't let the value 5 range like that. And what that means essentially is that the area associated with this is 0, because while it has a height, clearly, it doesn't have a width. The width is infinitesimally small, which means that essentially its width is 0. And that means that the probability that the random variable x is equal to a or equal to 5, or any number for that matter, is going to be 0 if you're talking about the probability that it's equal to that number precisely. Okay, so in other words, you need an interval on the number line to have any area that's non-zero, right? So if you want to talk about the probability that x is between a and b, that will have an area, and it will have a probability as a result, because area is going to be the same as probability. So area under this curve for continuous probability distributions will be equal to the probability, right? So if I find out that this area is 0.62, that means that the probability that x is between a and b is 0.62. Okay, so for those who took calculus, you can see this is an integration symbol, and we use integration to find the area under smooth curves like this. So we won't have simple rectangles where we could use basic geometry to find the area, but we will have calculus as a method to do that. Regardless of how they calculate the area, you want to make the connection to the area under the curve is equivalent to probability for continuous probability distributions. And again, we can ask questions like the probability that x is greater than b, that it's between a and b, that it's less than b, etc. But if we ask the probability that x is equal to b, the answer will be 0 because there is no width or no area associated with b. It has a height, but it has no width. So therefore the area is 0. Okay, that's important.